Okay, so continuing with lesson 4, we're going to be continuing to solve logarithmic equations. If you look at example 12, log base 3 of 4x minus 7 equals 2. If you notice, this particular equation only has a log on one side, but not the other. So it's not just a matter of, dropping your logs. You can't drop your logs when you don't have a log on the right or the other side. So what we're looking for, if you think about it, is the value for x that would make this expression what? Well, this is where you just go back to your definition of a logarithm. Remember the very first lesson, I guess it was lesson 2, not 1, where we took a logarithmic expression and wrote it in terms of an exponential expression. That's where we would take the base, raise it to the second power, and set it equal to that expression right there, 4x minus 7. So here's an equation where we have a logarithm on one side but not the other. So all we have to do is rewrite this in exponential form to get rid of the log. And so that's 3 squared equals 4x minus 9. But this equation is just a linear equation, which gives me 9 equals 4x minus 7. Now just solve the linear equation and you'll have your value, hopefully. So add the 7, we get 16 equals 4x, and x equals 4. Now, you have to check to make sure that it's correct for the logarithmic equation as well. The 4 is a solution to this linear equation, but you have to check to see if it's a solution for the logarithmic equation. So let's see. If x is 4, what's 4 times 4? 16. 16 minus 7 is 9. So if we're checking this, log base 3 of 9 equals 2. And that's correct. 3 squared equals 9. So when you have a logarithmic equation, you just kind of have to analyze it and see what the situation is before you can decide how you're going to solve it. So here we have another example where we have a logarithmic equation where a log is only on one side and not the other. So that's when you should think of rewriting this in exponential form or convert it to exponential form to get rid of the log. And that would be x squared equals 64. And x squared equals 64. If we solve this for x by taking the square root, we get x equals plus or minus 8. All right, so now you have to make sure that both of these solutions that work for the quadratic equation also work for the logarithmic. Well, the positive 8 is fine. Log base 8 of 64 equals 2. But remember, log, the base of a logarithm, right there, it cannot be negative. So the base of a logarithm has to be greater than 0. So the only solution is x equals 8. Okay, so that's the purpose for checking your answers, because the solutions that you get they're going to work, well, they very well may work for the quadratic, or they may be the solutions that you get for this quadratic, but they don't both actually end up being a solution for the original logarithmic. All right, and we have another example 14. Again, we have a logarithmic equation with a log on one side and not the other. Let's just rewrite that. Or convert that using exponents. So I will have 9 to the power of 9 to the power of 3 halves equals x. Well, there's really no steps left involved to solving for x. Just calculate this. So remember, 3 halves. The denominator tells you to take the square root of 9. The square root of 9 is 3. Now take your 3 and cube it, and you get 27. So x equals 27. So 9, this log base 9 of 27 equals 3 halves. And that's true. So there's your solution. And that's, once again, rewriting or converting that logarithmic equation or expression to exponential form first. Now this is the last example in this set that's similar to those. We have log base 4 of x equals negative 3 halves. So let's take our 4 and raise it to the negative 3 halves power equals x. Well, this is just a matter of calculating what 4 to the negative 3 halves is. The negative is going to make me rewrite this as x equals 1 over 4 to the positive 3 halves power. And the 2 in that denominator tells me to take the square root of 4, which is 2, and then cube the 2, which is 8. So 1/8 is my solution to this logarithmic equation. Okay, so now when you have an equation where you only have a log on one side, as example 12, 13, 14, and 15, the key there is to rewrite the equation in exponential form, or convert it to exponential form first and then solve it. All right. So our next couple of examples are going to be examples where we have multiple logs and they're not necessarily on both sides of the equation. They might be, but they might not be. So these examples are going to include, are going to involve simplifying each side of the equation completely first before you try to, you want to get each side of the equation to be a single logarithm if at all possible.